In this session, we are going to start this departmental subject of thermodynamics. You know that this is one of the very important core chemical engineering subject, and it's common and it's having an interface with some common part with other branches of engineering and physics. So, here our focus over the entire course of this or the syllabus of this thermodynamics as far as it is concerned for GET will be, the first part will be the engineering thermodynamics, the basic principles, the first law, the second law, the different types of engines which converts effectively the heat into work, and additionally the closed loop systems like thermal power stations, then refrigeration plants, liquefaction plants, which are of specific importance with respect to chemical process plants. And the second half, the second segment will focus on the equilibrium, phase equilibrium relations, like majorly concentrating on vapor liquid equilibrium. Additionally, we will be discussing the liquid liquid equilibrium and the reaction equilibrium. You see that this thermodynamics, this is relatively a difficult subject from the conceptual point of view, as we do not have any geometric picturization of these subjects like heat transfer, mass transfer or fluid mechanics, where we can visualize something. Here it is entirely a subject which is based on pure logic, right, and it is, in a sense, it is abstract. So, and specifically when we are going for the classical thermodynamics, there are limitations, like we can't go for molecular picturization of that system, and we simplify that in terms of certain abstract variables or parameters, right, which in toto as such it is difficult to understand or perceive physically. So, this is basically the problems in this entire subject, and that is why the detailed and exhaustive understanding is necessary, such that we will be able to apply the essence of that subject in solving different chemical engineering problems, specifically pertaining to systems of mass transfer, where we need the equilibrium relations, or in other different units, like where no such phase separations or reaction is going on, like in heat transfer, like in compressor, in pumps, we have to view it from thermodynamic perspective, right. So, here we are going to start initially the engineering thermodynamics part, starting from the very basic definitions of introductory concepts in this class or in this session, and next we will try to apply this. Next, once we are exposed to the second law of thermodynamics and Carnot cycle, then we will proceed slowly to this steady flow energy equations and different heat productions or work production systems from heat, right. So, you see, whenever, not only in thermodynamics, whenever in fluid mechanics also, in heat transfer also, when we start, and actually these are all a part of those subjects, or every subject is basically, or classical domain subjects, it is basically a combination of thermodynamics, wherefrom we get the conservation principles, and what is beyond the scope of thermodynamics is the rate, that is kinetics, right. Rate of any process, like rate of heat transfer, rate of fluid flow, or momentum transfer, or mass transfer. So, these rate equations are at one hand, on the other hand we have the conservation equations, and if we couple it collectively and subjectively for a specific purpose, we are actually a subject evolves like heat transfer or mass transfer or fluid mechanics or even reaction engineering. right. So, here fundamentally we are going to start with the understanding of what is referred as system, right. So, thermodynamically a system means what we are trying to analyze, and we will demarcate it from the rest. Okay. So, you see that it's a kind of framing in real life situation, that it's a whole, and we have to focus on a specific part, right. So, it's a kind of segregation, it's a mental segregations which is actually will produce some ease in this analysis, and that's why we have to define a system, we have to fix a boundary between the system and the rest of the world, and that is the entry point into the subject of thermodynamics. So, you see system, anything we want to study or analyze, right. Now, you see it may be a definite amount of easily identifiable mass, which we have discussed in fluid mechanics, right. That may be a part, that may be a kind of system, or alternatively in case of flow process where we have a space and there is some inflow and outflow taking place, like that of the example of tank with which we have started the Reynolds transport theorem in fluid mechanics. So, that may be also a system in thermodynamic analysis. So, the system here, let us categorize it into two. First is the control mass, or definite amount of easily identifiable mass, or it may be a control volume, a fixed region of space, right. So, once we have identified the system, define a system upon constructing a boundary, upon constructing its boundary, right. So, this isolates our subject of analysis from the rest, right. So, we have to first isolate it out, we have to frame it out. Rest, the rest is surrounding, right. So, the interaction between the system and the surrounding and the property change of the system thereof because of that interaction is basically the fundamental focus of thermodynamics. So, we can also here state that system plus surrounding is giving you the thermodynamic universe, right. Definitely we will define surrounding is not indefinite space or indefinite region of the rest of the literal universe, literally the universe, it is not. Thermodynamic universe is not actually the universe, it is the region or the amount of matter to be included in the surrounding, up to which the effect of the system surrounding interaction is being felt, right. So, up to that we will define the surrounding, and that is why thermodynamic universe is a finite space or the finite amount of matter, right. It is not an indefinite, that actual universe itself. So, you see that just like if we are trying to analyze, say it is a bubble, right, a gas bubble moving through some liquid. So, we can think the gas, what may be the system, that depends on our analysis. We can think the bulk gas inside, locked inside the bubble as my system. We may think the liquid as my system. We may also think the interface as the system. The interface between the gas and the liquid, that interface may also be considered as our system, right. So, that depends on what we want to analyze. There is no fixed rule, okay. So, what you are trying to analyze, what you are trying to focus on is your system, and accordingly you have to define it, and the rest of this thermodynamic universe, up to which thermodynamic universe is a space or the material within which the effect of the system surrounding interaction is being felt. So, once we have defined the system, definitely there will be interaction between the system and the surrounding. The interaction will be majorly in terms of energy exchange and mass exchange, right, and or mass exchange. So, we can say that system surrounding interaction definitely it is exchange of energy and or mass. Now, we do not have any confusion, or it is totally elementary about what is mass, but we have to redefine this energy. The idea of energy we have to revisit when we are studying thermodynamics, right. So, you see, so next topic of discussion will be the energy. So, definitely the energy of a system is its ability to perform work, right, or we will discuss it in detail, but it is a very preliminary school level definition. So, let us more focus on the energy itself. So, energy, you see, in classical thermodynamics we will consider two forms of energy. One is macroscopic, another is microscopic. So, in macroscopic form, definitely we have the well known kinetic energy and the potential energy. The potential energy will be mostly it is the gravitational potential energy we are talking about, right. So, macroscopic energy forms consist of kinetic energy and potential energy, right. So, potential energy means here gravitational potential energy. Now, you see the kinetic energy of a body, the energy which the body possesses because of its motion, right. So, kinetic energy Ek, we all know this is half of mv square. Actually, the measure of kinetic energy, how we can measure it? When the body is moving with a velocity v and it has got a mass m, right, the work to be done by retarding force in order to seize the motion of that body is the measure of its kinetic energy, right. So, work done by retarding force to stop the body or stop this object is a measure of its kinetic energy, right. So, it can be very easily proved. Let us say an object is moving with a velocity v and it has got a mass m and we are applying a retarding force F, right. So, F will cause a deceleration. So, you can write that F is equal to, let us say this is x direction. So, minus of m into dv dx, right, into v. Minus of m, this F, the deceleration, we are actually considering its magnitude only. So, v into dv dx is the expression of deceleration or acceleration in general. We are putting a negative sign because it is decreasing. So, and there the velocity and the force are in the opposite direction. So, we have to go for a sign match. So, m into dv dx into v. So, f dx integral say 0 to L will be the work, and that is equal to m v dv. Initial velocity v, final velocity is 0. So, it is giving you half of mv square. So, that is the work done, which is a measure of kinetic energy, right. Now, gravitational potential energy, as you all know, here the force is m into g, and from a datum z equal to 0, if you are lifting that object by a height h, right. So, the work done in order to lift against the force field of gravity will be definitely mgh. So, these two are the macroscopic forms of energy. Now, considering the microscopic form, again you see that when we have studied fluid mechanics, we have talked about the fundamental assumptions of fluid mechanics as the assumption of continuum, right. Now, you see the continuum means there is no molecular or atomic aspects of that material. We are negating these atomic aspects. We are thinking that object is a continuous distribution of matter. Actually, that assumption of continuum is a common assumption to all classical subjects, right, like also in classical thermodynamics. Now, when if I think it from that perspective, if we are negating this molecular aspect, then actually we have to negate the molecular modes of energy, right, because inside a piece of metal there are free electrons which are moving, there are Coulombic interactions, there are electric or magnetic dipole moments, and because of all these we have a molecular or microscopic energy, right. Now, if we are considering the assumption of continuum and we are taking this up, we are negating the molecular perspective, but if we negate all these molecular forms of energy, there will be mismatch and error in the energy balance. So, all these microscopic modes, possible modes of energy, we will lump into a kind of energy form, and that we call internal energy, right. So, internal energy we will think it is a kind of macroscopic attributes even, right. It is a macroscopic analog of all microscopic modes of energy. Now, what are the microscopic modes of energy? See, microscopic modes of energy. So, it is molecular translation pertinent in gas and liquid, molecular rotation, molecular vibration, electron translation, electron spin, nuclear spin, then we can think of Coulombic interaction, molecular binding, nuclear binding, intermolecular forces or intermolecular interaction, electric dipole moment, magnetic dipole moment, mass energy equivalence, and also external field other than gravity. Right. So there are different modes of microscopic forms of energy, and each individually for molecular pair or electronic pair or for individual molecular electron, even if it is insignificant, but if we calculate it for the entire bulk of material, it is definitely significant. So what we do? We cannot individually go on calculating the energy, right? So lumped approach. So all are lumped into something called internal energy, right? U. So once we are lumping it, we actually lose the scope of calculating the absolute value of the different forms, because as we are not individually calculating the forms of energy, we are simply lumping it. So internal energy, if I want to calculate, we have to know the individual mathematical forms, right? Or we have to go by a different molecular thermodynamic approach, which we are not using here in classical paradigm. So in classical paradigm, we have to understand that we can calculate the change of internal energy by macroscopic balance. However, we cannot calculate the absolute value of internal energy, right? So as we are doing it, the consequence is calculation of U cannot be, or it's impossible. Calculation of absolute value of U becomes impossible, right? However, we will work with that. We will satisfy ourselves, okay, we are able to calculate only the change of internal energy, but not the absolute value. It's fine. But at least in this gross energy balance, in the macroscopic energy balance, there will be no such problems of mismatch, which was initially there before lumping, right? So total energy, once we have lumped, the total energy E, it's basically U plus Ek plus Ep. This is the total energy. Right. So you see, we have defined the total energy of the system as a lumped macroscopic form and the two other lumped microscopic form, which is internal energy, and two other gross macroscopic form, which are kinetic and potential energies. So, with that we will proceed with the energy interactions between the system and the surrounding. So, you see, when energy is transferred, right, it can be transferred in pure form, like without any mass exchange, or whenever there is a mass exchange, mass flow in or out, there will be energy transfer, because individually per unit mass of the system and the surrounding, definitely that material consists of certain energy, right. So, from this perspective of this form of energy transfer, that is whether it is pure or it is associated with mass exchange, from that perspective we can define a system, right, as open, closed or isolated. Energy and mass transfer perspective. So, this leads to classification of a system into three categories. Number one, closed system. Energy exchange is permitted without any mass exchange, right. Typical example which we will consider as a model in closed system analysis, that is a gas enclosed in a piston cylinder assembly, right. So, we have a cylinder fitted with a piston and we have a gas. So, the gas, which is a control mass, is a closed system, because it may be heated, right. Let us say there is a heater placed here. So, it may be heated and it can displace the dead weight of the piston, so it can perform work, right. So, this is a typical example of closed system. Second, it is open system, where both mass and energy exchange are permitted, right. So, typically it is the same example, maybe a tank fitted with a heating coil, right, inflow and outflow. So, it is open system. And here the corresponding system must be what? It is a control volume. It can never be a control mass, because it will not lead you to any tangible outcome. It should be a control mass. So, here this we can define as our system surrounding boundary, and here this will be the control volume. Sorry, control volume, not the control mass, it must be a control volume. So, first it is closed system, next it is open system. So, third is isolated system. As you can understand that neither mass nor energy exchange is permitted. Example, if we have a insulated, highly insulated container in which some gas or liquid or some solid is locked in, that may be an isolated system. Alternatively, the easy and universal example of isolated system is a thermodynamic universe, right? So, we say that thermodynamic universe is an isolated system. Right? So, from this mass or energy transfer perspective, we have defined the closed system, open system and isolated system. Now, energy transfer only, energy transfer without mass transfer if I think there are two possible modes. One is either the energy, or rather we can write this energy as it crosses the system surrounding boundary will either assume the form of heat or the form of work. So, this heat and work, they are forms of energy in transit. Right. As such, the system cannot have or cannot contain heat or work. Right? It contains energy. When it exchanges only energy without mass exchange with the surrounding, it will exchange it either in the form of work or in the form of heat. Right? So, we can't say that the object or a specific amount of material or a control volume is having heat. It's not, it's meaningless statement. It's having energy. Whenever it is exchanging heat with the surrounding, it will assume the energy will assume either the form of heat or the form of work. See, we will discuss the heat and the heat exchange, how it can be measured and everything. But we have the empirical law of calorimetry, which states that heat given to a system or heat taken away from the system, we know it as mCp delta T. We will discuss it later. But for the time being, let us focus on work, or a special type of work which is a pressure volume work. There are different forms of work in addition to pressure volume work, but when we begin the thermodynamic analysis, we actually start our discussion with the most easy form of work, that is the pressure volume work. A common form of work, that is a pressure volume work. We can also have works pertaining to these other forms like interfacial. We can think of work in this magnetic force field, in electric force field, or different other forms of works are also possible, right? But here we are not going to discuss that. Okay? We are focusing on specifically on pressure volume work, and that is the central work category what we consider in all engineering thermodynamic analysis. So, you see this work, if I want to calculate the pressure volume work, let us think how we can write that. Okay. And here I want to probe in with this statement that we have a wrong idea that pressure volume work is P dV. It's not. Okay? It's P opposing dV. The work expression in pressure volume system. Like the typical example will be the gas enclosed in a piston cylinder assembly, right? Let us say this is state 1, okay, of the gas or the system. This is state 1 where we have a massless piston and a mass m, deadweight m on it, massless piston, right, and we have latch. And the system has got a pressure P1, volume V1, temperature T1. In the next instant, when we are removing the latches, the compressed gas will release the pressure and lift the deadweight by a height h. Let us say in this state the pressure P2, volume is V2, temperature is T2. So, this is state 2 of that system, right, and we want to calculate the work W12 between the state 1 initial state and the final state, right. So, W12, how we can write that? So, basically if we do not think from the expansion of gas, but from the lift of this deadweight, we can easily understand that actually we are giving through this gas, work of the gas, we are imparting a potential energy on this deadweight and it is lifted by a height h, right. So, obviously it is mgh, the work done, the force multiplied by the displacement. Now, in order to convert it in consistent variable which is pertaining to the variable of the gas itself, we will do what? We will divide this mg by area of that piston and multiply this h by area. So, here mg by A is neither, it is not P1, right, because the pressure of the gas is progressively changing. It may be equal to P2 because in this state it equilibrates with this opposing pressure. So, mg by A is the opposing pressure against which the gas is expanding. So, we will write it as P opposing into delta V, and delta V is equal to V2 minus V1, right, and that is W12. So, in differential form, if I want to write that, we will use this symbol to represent the differential delta, and here it will be P opposing into dV, right. So, naturally the question arises, as you know also, that why we have used delta sign to represent the differential of work and sign d, which is conventional, to represent the differential of volume. So, definitely work and volume are two different types of variable, thermodynamic variable, right. So, this we call path variable and this volume we call state variable. So, we will continue our discussion with the understanding of state variable and path variable, right. So, you see that in all thermodynamic variables, there is either a state variable or a path variable, right. So, what do you mean by the state variable? You see, the state variable means only depends on the current state of that system, state or rather condition of the system, and independent of the fact that how the state has been achieved. How the state has been achieved, it's independent of the fact, it only depends on the state, right. So that's why it is called state variable. So typical example of state variables, definitely it's pressure, volume, temperature, internal energy, or any other possible combination of state variables of primary state variables. Like if I write u squared divided by v into t, that's also a state variable, it's not a path variable, right. Now, contrary to this state variable, okay, let's have a discussion in relation to the state variable, though it will be qualitative mostly. See, immediately we can ask the question that, okay, I have defined the state variable, fine. Now, how we can define a state of a system, or to specify the state, how many state variables are necessary to be specified? To define, so obvious question, to define a state of a system, how many state variables are required? So the answer is, though it is discussed and elaborated later, the answer is number of state variables required is equal to the degrees of freedom of the system. Right. And you know the degrees of freedom, the number of variables minus number of equations. So degrees of freedom is defined as number of variables, or rather independent variables, or rather number of variables minus number of equations, right. And this is a general definition of degrees of freedom, but in thermodynamic analysis this has been reduced to, we will discuss and prove it later, the Gibbs phase rule, which states the degrees of freedom for a multi-phase multi-component system is C minus P plus 2, right. C, the number of components, P, the number of phases, and 2 for temperature and pressure, baseline value. Now, what is a baseline here? For pure and homogeneous system, we need only two state variables, right? That's why there is 2 here. Now, as we go on increasing the number of components from 1 to 2, 3, 4 and the number of phases, you go on increasing it, so you can calculate the degrees of freedom. Just like here, for pure and homogeneous component, here you see the number of variables: pressure, volume and temperature, and we have number of equations that's equal to 1, that is the equation of state. We know the ideal gas equation is an equation of state, and that's equal to degrees of freedom. So it is 3 minus 1 equal to 2, right? So you see that Gibbs phase rule is exactly consistent with a pure and homogeneous system, and for that we have 2 here, right? That's for pure and homogeneous single phase, single component system. And next, as you go on adding more phases and more components, we have to change that formula for the degrees of freedom into C minus B plus 2, right? Now, question is, what is a phase? Phase, by the way, here, phase is what? Phase we can define as a homogeneous part of a system. That's phase. The basic definition, right? The homogeneous part of a system is the phase. So when the homogeneity is lost and second level of homogeneity begins, that is another phase, like from gas to liquid or from liquid to solid, etc. So you see that in relation to the state variable, we have defined what is state variable, and we have also fundamentally answered the question that how many state variables are necessary to represent the state of a system, right? And that's exactly equal to the degrees of freedom, and which we can calculate from the Gibbs phase rule. Okay? Now, whenever the system exhibits a process, that means a change of state from state 1, let's say, to state 2, right? So you have to represent that process at least upon specifying the initial and the final state. So how to represent a change of state? At least upon specifying the initial and final state in a pertinent diagram, right? And what will be the pertinent diagram? This pertinent diagram is the phase space of the system, right? It is a phase space, and definitely it is a space which should have the dimension same as that of the degrees of freedom, right? So here from we have to understand that dimension of the phase space is equal to degrees of freedom of the system, right? So the dimension of the phase space is same as the degrees of freedom of the system. It's obviously perceivable from the common logic, right? We are not proving it rigorously, but from the basic understanding we can say that, okay, I have to represent the state upon specifying the number of state variables which equal to the degrees of freedom. So definitely in this pictorial representation, if I just mark it as a point, the respective space should be the phase space. It should have the same dimension as that of the degrees of freedom of that system. Now, on here and from here, what are the state variables to be chosen to represent the state? Because we know that for a pure homogeneous system, we have just concluded that, or we have just stated rather, we have not proved or just justified, or we have justified at least, but we have not rigorously proved it. There are two number of state variables. So, what are they? Whether it will be pressure, temperature, or pressure, volume, volume, temperature, what are they? Right. So, the answer to this question is we must choose state variables which can be directly measured. Right? We don't have to calculate it from this measurement, like pressure and temperature. Right? Not volume, not that. Okay? Not volume. Because volume you have to calculate upon applying the equation of state. Volume cannot be directly measured. Like it's not, do not confuse it like I have gas enclosed in a piston cylinder assembly. I know the volume, right, from the position of the piston. It's not that volume we are talking about. It may be the molar volume of the gas, right, which you cannot measure directly. You have to measure the pressure. You have to measure the temperature of the system, you have to know the type of gas, and you apply the appropriate equation of state for that gas, knowing the individual parameters, right, and from there you calculate the molecular or molar volume. Okay. So, volume is to be calculated from the pressure and temperature, but if you insert a pressure gauge or a thermocouple in this gas, so you can directly get the reading of pressure and temperature, right. So, these variables which are most easily measured, they are primary variables, they are referred as primary variables of the system or canonical variables, right. So, we will discuss and elaborate on that, but before going into this phase space construction or phase plane construction. So, just statement here will be helpful to understand the phase space. See, we will go for a two-dimensional space for representing the process executed by a pure homogeneous system, right. So, according to our conclusion, it should be PT space, but rarely we use PT space in classical textbooks of thermodynamics. We change it to PV space. Instead, V is not a canonical variable. Why? Because we want a physical feel about that system, like gas is expanding, right. A gas, it's expanding. So, we have the idea that okay, the volume will change, but immediately how the temperature will change, we have to think that okay, as it is expanding, the gas will cool down, right. So, if we represent the initial and final points, we have to think about it, what is the type of the process being executed by the gas. But if we represent it in PV space, like one point is here, state 1, another point is here, we can surely say that okay, it's a kind of expansion, right. But in PT space, we have to think and it's a bit difficult. So, anyway, the thing is, that's why even the volume is not a canonical variable, we choose volume to represent the process executed by a pure homogeneous system. So, once we have defined the state variables, next obviously it is the path variable we have to understand. So, you see the path variables, it is what? It depends on the path, right. Like in a PV space, if I have the initial state 1 and final state 2, and let us say we are able to trace the path, how we will discuss later. Say this is path 1, this is another path going to the same final state, path 2, and this is another path which is path 3, right. So, you see that delta u 1 2 for path 1 is delta u 1 2 for path 2 and delta u 1 2 for path 3. Same is true for pressure, volume, temperature, etc. All other state variables. However, Q121 is not equal to Q122 and neither it is equal to Q123. Same is true for work. So, Q and W are path functions or path variables, right. They depends on the path, how the state is being achieved, not only on the final state. Okay. So, that is why they are recognized as path variables. So, thermodynamic variables, there are two different types, path and state variables, right. And regarding in relation to the state variable, we have got the idea of the degrees of freedom, phase space, canonical variable, etc. Now, immediately we can think of this question that can we propose a relationship between the change of the path variable, the change of the state variable and the associated path variable. So, the relation between path variables and change of a state variable. What is that? The first fundamental relation is the first law of thermodynamics. Right, is the first law of thermodynamics which relates the change of a state variable to some difference of the path variable. What it states? See, I have a system and here we have to specify the sign convention. If Q amount of heat is given and Q we consider positive if heat is given to the system. And work considered positive if performed by the system. Right. So, the first law is alternatively a conservation law of energy. What it states? That Q, heat given to a system, a part, will be used to increase the internal or increase the total energy of the system. It is not internal energy, it must be the total energy, right. Total energy of the system, and the rest will be used to perform work. Okay. So, that is the general form of the first law. Now, for closed system, when there is no exchange of mass, right, the change of kinetic energy, the system is not moving, right. Generally, delta Ek, change of kinetic energy, delta Ep, that is equal to 0. So we reduce it, Q is equal to delta U plus W, but that's not the general form. General form is this. Okay? So in differential notation, we can rewrite this first law as del Q, the differential sign to represent the path variable, equal to dE plus del W, another path variable. Correct? So that's the first law of thermodynamics, and you see that the same law we can actually state that this is conservation law of energy. Right. Now you see what is conservation law? What is the general conservation law of energy? That E universe is constant. Right. So del E universe is 0. So del E system plus del E surrounding, it's equal to 0. Right. So how we can establish that? You see, let's apply first law for the system. The form we have written, that Q is equal to delta E system plus W. Let's say this is work done by the system, heat given to the system. Now for surrounding, if we write the same law, Q surrounding is equal to delta E surrounding plus W surrounding. Right. Now if I add, heat given to the system must be abstracted from the surrounding, right? So Q system is equal to minus of Q surrounding. Add, so you will get 0. So this is delta E universe. And work, see, work done by the system is the work done on the surrounding. So W system is equal to minus W surrounding. So this is also 0. So exactly it corroborates with the conservation law of energy. So in relation to this, before we stop this session, it's important to introduce another state variable of importance, a new state variable of importance. It's enthalpy. Right. And actually we will see later that through this enthalpy we can justify the empirical law of calorimetry, that Q is equal to mCp delta T. We will justify that. Right. So enthalpy is defined as U plus PV. As I have mentioned, that any combination of linear, nonlinear, any type of combination of state variable will be giving you another state variable. So enthalpy equal to U plus PV. So just that, so we can write that dH is equal to du plus PdV plus VdP. So just this definition you note, and with that we will later relate this Q to this delta H, considering a specific type of process called reversible process. And to understand the reversible process, we have to understand what is the thermodynamic equilibrium. So we will discuss it in the next session. Thank you.